Okay, so I'm going to start out with asking you guys, the three of you that are logged on with me right now. Do you guys have any specific questions? I mean, I can go over some of the questions that I think might be relevant on the last two assignments, like 5B and 5A. They cover a t-test. It's kind of like, they also a bit involve confidence intervals as well that I presume will come up. But if you guys have any specific questions right now, let me know, and I will go ahead. Otherwise, I'll go ahead and just get started on some stuff that I think will be relevant that may show up on the test. So let me know. You can go ahead and type into the chat box if you don't have a question right now. But let me open up this document that we had, which was the practice questions. Okay, they have a number of solutions in them already, I know, but let me just go through them and see what we have that's of interest here. We have a number of questions that involve proportions. We didn't do that many of them in class. We did a couple of them, I guess, between class and homework, but there seem to be a number of them here. And then there's a lot of single sample t-tests that we see here as well. Not so much in the practice questions, not so much two sample t-tests. I don't think I didn't see that many questions on that. Let me get to something a little bit more challenging. Let's see. Okay, let's see. Oh, I highlighted something here. Maybe I have a different document that I highlighted. Maybe it's this one. Okay, let me start with problem number 5. Okay, it involves some numbers. Then I'll go on to one that involves a proportion. Survey is taken to estimate the mean annual family income for families living in public housing in Chicago for a random sample of 29 families. The annual incomes in hundreds of thousands of dollars are these numbers. Construct a box plot or histogram of the incomes. What do you predict about the shape of the population distribution? Does this affect the possible inferences? Using SPSS or Excel, find a point estimate of the mean income and the standard deviation for all the families living in public housing. Calculate a 95% confidence interval for the population mean. Okay, so I'm going to start with this first part. Construct a box plot or a histogram. Well, it's going to be a lot easier if I do that in Excel, SPSS, than if I do it some other way. But I'm gonna do this the hard way now. I've imported. Actually, just so you know that you can do this. These numbers are separated by tabs. So if I highlight them all and say copy, Control or Command C, and I go in here and I say Control V or paste, they'll actually paste into the different boxes because Excel likes working with comma delimited data. I've already done that, so I'm going to undo that paste. But that gets them in there pretty well. The other thing I'm going to do is I'm going to cut this out, and I'm going to paste it down here. I don't really need to do this for any calculations that I do in Excel, but I know later on I'm going to want to import this into SPSS. So SPSS wants all the values for a particular variable. In this case, the annual income. It wants all those values in a single column. Okay, that one I guess I Control C instead of. Let me just Command X and 94 down. Okay, good. Got them all in there. Okay, so one of the things we asked for was, I'm going to work backwards a little bit on this. One of the things we asked for was calculate using SPS or Excel, find a point estimate of the mean income and the standard deviation for these families. Calculate and interpret a 95% confidence interval. Okay, so it looks like there's 29 families here. So we still consider 29 families. We would consider that a small sample. Okay, so I know I'm gonna have to be using the t-table for this to have a confidence interval. But first I'm gonna find the mean, right? So the mean, another way of saying mean is x bar, x with a bar on top, right? That's gonna be equal to the average of all of these numbers. Okay, and it comes, oops, I did something wrong there. Oops, I misspelled average there, didn't I? Okay, there's my average. And now I'm going to want to calculate the standard deviation of all these numbers. I'll call that S. And that's going to be equal to the standard deviation. It's kind of all these numbers. And that's equal to 20. Standard deviation is equal to 20. There's quite a bit of variability there, right? So 64,000 up to 139,000. So it's a pretty wide range, right? So, okay. So now I have a point value for the mean of this sample, and I have a value for the standard deviation of the sample. I don't know those values for the population, right? Like everybody in public housing in Chicago, right? Which might be tens or hundreds of thousands of people, right? So I don't know what mu is, and I don't know what sigma is. I'll have to type it out so I don't spend a lot of time looking for it on the keyboard or in the control characters, right? So I don't know what these are, right? But I do know that I can estimate them based on the sample mean and the sample standard deviation. So now I want to calculate a confidence interval. And the way I calculate the confidence interval is I start with the mean. It would be wonderful to be able to start with mu, right? But we don't know that, so we start with x bar. And then we're gonna have an interval around that, plus or minus. Okay, the standard error, right? For that particular sample size, the way that samples of this size 29 would be distributed with this amount of variability. So now I would want to multiply this by the value of t or z. Z if it's a super large sample, t if it's a small sample. The value of the t distribution for that particular sample size times the standard error for samples of size 29 from this population. Okay, so now what is that going to be equal to? It's going to be, I'm going to put x bar in here first. That's equal to this number, right? And the t value of t for a sample size of 29, well, I'm going to have to look that up. I'm going to look that up across the t table. Okay. So for a 95% confidence interval, the value that we're looking for is going to be, let's see, 29 is a sample size, 28 degrees of freedom would be 2.048. So that value would be 2.048. So here's x bar. Here is our value for t for n equals, for degrees of freedom equal 28. Okay, and what's our standard error now? Now, standard error is going to be equal to, it's going to be equal to sigma, the population standard deviation, over the square root of the sample size. Okay, now we got a problem right off the bat, don't we? We don't know what sigma is. So we're going to use the standard deviation of the sample to represent sigma. That's one of the reasons why we had to use the t-distribution instead of the z-score of 1.96 for a 95% confidence interval. So let's go ahead and calculate this. The standard error is going to be equal to the standard deviation divided by the square root of the sample size, which is 29. Okay, that comes out to be 3.895. 3.898. Okay, it's equal to this number. Okay, so now that I have x bar, the value for t, and the standard error, I can go ahead and calculate my confidence interval. I'll bring it down here. So what is it going to be equal to? It's going to be equal to 90.24 minus the value of t times the standard error. Okay, now this will multiply first and then get subtracted. So it should work out okay. I don't think I need parentheses. Okay, and that's my lower value for my confidence interval. And so now what's my upper value? My upper value is going to be equal to x bar, 90, plus 2.048 times the standard error Oh, did I forget to put I forgot to put a equal sign in there. That's why it didn't follow me along. Equals 90 plus t times the standard error. Okay, so there's my confidence interval, right there. So we've got most of what we had been looking for in that first part of that problem. Let me go back to Word. Okay. And okay. I'm gonna check. I see you have a question there. Good. I'll address that. Using the Spss find a point as okay. Point estimate of the mean, the standard deviation, calculate 95% confidence interval for the mean. So what we've just calculated is a range, two numbers, and we're 95% sure that the true mean, mu, lies between these two numbers. Okay, so let's go back and see what else it asks for. It asks for a box plot or a histogram of the outcomes. Well, the easiest way for me to do that is going to be to go to SPSS and have it and import this data and have it create a histogram and a box plot for us. If we want to do it manually, we would have to break this up into frequencies. In other words, how many people, how many families had incomes between 60 and 70,000, between 71 and 80,000, between 81 and 90,000, so on and so forth, to draw a histogram. To draw a box plot, I would have to find the percentiles that are involved here. Like, for instance, if I wanted to know where the, if I'm going to draw a box, yeah, I'll do it this way. If this were going to represent the 25th percentile and 25th percentile and 75th percentile, in other words, our interquartile range, and this would represent our minimum and our maximum. Well, down at the bottom here would be the lowest number, which might be, I'm guessing, 60, right? And at the top here, that little feather at the top would be our highest number, which I'm guessing is 139. But what are these bars here going to be? Well, this is the 25th percentile. You can actually calculate that. That's equal to percentile. And I put parentheses in, and it wants the array, the numbers that we want to find the percentiles for, comma, the array, comma, and the percentile, which is going to be 0.25. Put it in as a decimal fraction. And that number is going to be 90. So that middle bar here, the bottom bar is going to be 90. I could do the percentile again for 0.75, use 0.75 instead of that, and then find the upper bar of the box plot. But we're going to do it in an easier way anyway. Okay, before I move on from here, the p-value by hand. You really can't get the p-value by hand. You can find the p-value if it's a very large sample and you are using z, right? You can find the p-value for a different, for instance, if you're evaluating, if you're doing a t-test and you're comparing a mean x bar 1 minus x bar 2, and that's over the standard error, however that's calculated. If you're calculating your z-score, right, it's a very large sample and you're assuming that's a z-score, you can use the normal distribution table to find out what area is represented by z. So I'm going to go over here, regress the z table. Okay, so for instance, let's say the z-score were let's say 2.5. Okay, so what p-value would that represent? So if the z-score is 2.5, could be, that's the distance from the mean, right? So we could look at it from the left side, which would be minus 2.5, or we could look at it from the right side. It can be a little bit simpler to look at it from the left side. So 2.50 would represent an area of 0.006, right? 0.6%. That means that 0.6% is to the left of that value, z-score value of 2.5, right? So now, since most of the time we're doing a two-tailed test, if we got a z-score plus or minus of 2.5, we would say, okay, that means that the likelihood of getting that outcome, if the null hypothesis is true, In other words, if we're wrong, if we reject the Null Hypothesis, it's less than 1%. It's only 0.6%, 0.006. But I also have to account for the fact that I could have gotten a value that was, even just simply by reversing x bar 1 and x bar 2 and doing x bar 2 and x minus x bar 1, you could have gotten a positive number as well, right? So in fact, if you're doing a two-tailed test, you want to add together the 0.006 here and a 0.006 here and say, okay, that's going to add up to 1.2% or 0.012. So in other words, if you have a z-score of negative 2.5 or positive 2.5, and you're doing a two-tailed test, that means that you have 1.2% chance of that value, that difference, that big a difference, occurring if the two populations have the same mean. In other words, if in the case that you would be wrong if you reject your null hypothesis. Okay, so that's kind of the way that we do this. On a t-test, let me bring up the t-table. Okay, if I bring up the t-table, on the t-table, we really don't have that opportunity to, oops, wrong. Let me use, if I start with Agresti, the name of the textbook. T-table, good. Let me bring up that table. If I bring up that table, it doesn't actually show me the areas. What it does instead, so I have it here, there it is. What it doesn't, no, that's not it either. That's it, there we go. Oh, it is. Oh, that's a Z table also. Where did my T table go? Oh, let me try it again. Is it down here now? Yeah, here we go. Here's the T table. Okay, so if I bring this up instead, each different situation that I go into, see if it's a sample of size 16, what the t-table tells me, it tells me is how big the z-score has to be, the t-score, excuse me, has to be in order to reject the null hypothesis. That's my critical value. My t-score that I calculate has to, for a sample size of 16, has to be bigger than 15 degrees of freedom, has to be bigger than this number in order for me to reject my null hypothesis. All that tells me now is that if my t-score that I calculate is bigger than that number, then my p-value is less than 5%. It's less than 2.5% on each end of the tail. In other words, 5% altogether. Okay, but it doesn't tell you what the exact p-score is, right? For that, you need Excel or you need SPSS. And I'm going to now try this again in SPSS. I'm going to do this. I'd have to erase all this, but I'm just going to copy these numbers and paste them into SPSS. That'll save me a little bit of time. If I erase these numbers, I can go ahead and import it from the Excel file. But I think this will work out a little bit quicker. Okay. Let's give it a moment of bouncing up and down. And then we'll take a look at something else. Okay, don't need that. So I'm just going to paste in these numbers. I'm going to let it have the variable named VAR that is assigned automatically. So now in SPSS, I can say analyze. I can say descriptive statistics. Now, if I say frequencies, I won't be right, will I? Because frequencies is intended for categorical data. In other words, it wants to count the number of occurrences for each thing. In other words, that would be okay if you're looking for gender. How many males are there? How many females are there? How many ones and twos are there, right? Or if you wanted to count ethnicities, how many Hispanics are there? How many whites are there? So on and so forth. So if I put this in here and I say okay, it's going to come up with kind of a bunch of nonsense. It's just going to list all of them because there's actually not there's only one of them that's duplicated, the 92. So frequency is really not for numerical variables. It's really for categorical or nominal variables. Okay, so instead I'm going to go to Analyze Descriptive Statistics. If I go into Descriptives, it's going to be helpful. I'm going to move my variable into my workbox. Options, say, okay, mean. I can tell it to calculate a bunch of stuff. Not everything, but a bunch of stuff. Click OK. And the calculation will occur, and it'll find my mean for me. Where is it? There's my mean, there's my standard deviation, there's my variance, a range, minimum, maximum. But it really didn't give me much other information. It certainly didn't give me a confidence interval. For that, I'm going to go into Analyze, Descriptive Statistics, Explore. Okay, when I go into Explore, now I'm going to tell it to, okay, go ahead, move that into my workbox, dependence list. And under Statistics, oh, look at that. It's ready to calculate the confidence interval for me. It wants me to know, it's asking me what kind of confidence interval do you want? 90%, 95%, 99%. I'm going to leave it at 99. And I'm going to go ahead and click OK. Well, let me see, maybe before that, I'm going to have it do a histogram because I think the question asked us to produce a histogram. I'm going to click OK. I'm not going to tell it to do a box plot because when you go into Explore, SPSS by default will create a box plot. So you'll see that in a second. So I'll click OK. Okay, so let's see what we get here. Okay, so now we got quite a bit more information, don't we? We have the mean, the median. Let's see, the mean, the median, the variance, the standard deviation, the confidence interval. Is that the same as we just calculated? Let me see if I can't superimpose this. Let's see. Okay. Our confidence interval was 82.25. Yeah, it looks like it's pretty much the same, doesn't it? The confidence interval. Okay, here's our mean here. I'm not sure what 5% trimmed mean is. I don't think I've ever used that for anything. The median, that's the middle number, the variance. So it looks like the same numbers that we got before. And here is our histogram. It looks fairly normal, right? Not perfectly normal, but fairly normal. And here is our box plot. Okay, let's take a look at our box plot here. One thing I noticed right off the bat is there's a value here that's an outlier. So our distribution is a little bit skewed. There's a value that's a little bit further away than we would want it to, than we would expect it to be, given the distribution of the rest of the numbers. That must be that very high income, $139,000, very high for low-income housing anyway, right? So what else do I see here? Well, I see that basically this is the median, which is this black bar in the middle, is pretty close to the middle. So that would suggest to me, and the minimum and the maximum, that suggests to me, except for the fact that we have this outlier, that this appears to be a relatively normal distribution. If it were really badly skewed to one direction, the median might be closer to the top or closer to the bottom. You can see it's skewed a little bit, which we expected, but it's not severely skewed. And you'll also notice that if you want, you can find the 25th percentile and the 75th percentile or your interquartile range. Okay, and there's your histogram as well. Okay, so that's how we might handle something like that. Let me go back to this page. Now, the other thing you might do with this data is that you might say to yourself, well, gee, let's go back to SPSS. And let's say we want to use SPSS to calculate a one sample t-test. Let's say you wanted to say that public housing, the average for public housing in New York is 100. The average income for public housing in New York is 100. This is let's say it's lower. Let's say it's 78,000. You remember what the mean was here? I think it was not. Was that the median or the mean? Let me go back and take a look at our output window. Okay, it appeared for us that the mean income was $90,000. So now I'm going to tell you that this is based on a survey, a random sample of 29 families. I'm going to tell you in New York, we actually know the values for all families in New York, and it happens to be 85,000. Well, this 90,000 is more than that 85,000, so it would suggest to me that the mean income in New York is lower than it is in Chicago. So I might say to myself, let me actually do a test for that. I know the mean in New York. The mean in Chicago, I'm basing on a sample. That's why we call that a single sample t-test. I'm not sampling New York, and I'm sampling Chicago, but I'm not sampling New York. I know what the mean is for New York. So I'm going to go ahead and say analyze, and I'm going to go to compare means, and I'm going to say I want to do a single sample t-test. Okay, and in this I'm going to say that here's the variable representing the salaries, the incomes for families in Chicago, and I'm going to say I want to compare that to the value from New York, which is 78,000. Okay, so let me see options. Again, if I want my alpha to be 5%, I want to have less than 5% chance of being wrong, or I want to be right 95% of the time. I'm going to leave that at 95%. So I'm going to go ahead and do this t-test. So now the t-test comes up, and it says, wow, what do we have here? We have a t-value of 3.1, degrees of freedom 28, and as it happens, we know that the critical value that we need to reject the null hypothesis. But now, what was the null hypothesis? Null hypothesis was that the mean in New York is equal to the mean in Chicago, right? And the alternative hypothesis is that they're not equal. And that's two-sided. We didn't bother to say whether one was more or less, but just that they're different. Okay, so I remember when I looked up the t-value for 28 degrees of freedom, I needed to exceed the value 2.04, I think it was. And in fact, I got a value of 3.1, so I know right off the bat I can reject the null hypothesis. The two means are different with 95% certainty, with alpha less than 0.05. Okay, but if I go further over, SPSS actually tells me what the probability of getting a t-value that large is if there's no difference between the two populations, and that making us wrong to reject the null hypothesis, and that two-tailed significance or p-value is 0.004. That means that 0.002 is on one end, 0.002 is on the other end, for a total probability of 0.004. Pretty low, right? Okay, so I can reject the null hypothesis there. Now, had this been two different samples, and I'm going to do this, copy, and I'm going to go back in here, and I'm going to paste it. Okay, I'm going to change a couple of numbers. I'm going to make let's see, I'm going to take that, make that 90. I'm going to take this and 64, make that 90. I'm going to make the 100. I'm going to make that 65. I'm going to make this 65. So I change these a little bit. Okay, so now let's say that these are two. This is New York and this is Chicago, or Chicago and New York. Okay, so now I want to compare. I have a sample from New York and a sample from Chicago. Different sample sizes, right? I missed a couple of boxes there. Let's say I wanted to compare those two variables. Okay, so the way I would do that, if I wanted to compare those two values, well, in SPSS, it really doesn't work this way. In SPSS, the way it works is that it wants to see the identifier in one column and the value in the other column. Okay, this would only work if it's Chicago before and after some intersection, right? So this is this is same family before and after, same family before and after, and so on and so forth. So I need to structure this a little bit differently. And the way I'm going to do that is I'm going to put in numbers here I'm going to say that 1 represents Chicago. Oops. Number 1 represents Chicago. And I'm going to go all the way down here. Okay. Okay, so those all represent Chicago. And now I'm going to take all of these numbers that I created here. And I'm going to cut them. And I'm going to paste them down here. Okay, and those are New York. And they're all going to be represented by 2. Oops. Good. Got them all. Okay, so now I'm going to go here and I'm going to delete this row here. Okay, so now I got variable 1 and variable 2. Well, variable 1 is the income. Whoops. Income. Okay. Income for Chicago. And variable 1 is the income period. And variable 2 is the city. Okay, so variable 2 is a nominal variable, right? So I can tell it by going into values that 1 represents Chicago and 2 represents New York. Okay, hopefully on a test this will kind of be formatted for you. You'll have a data set already. You won't have to go through this, but just so you know that, for the future if you need to. So what do I have here? I have one column which represents the variable income of families, second column which represents the city that they live in. Okay, and some of these people live in Chicago, some of these people live in New York. Well, let's go into Analyze, Descriptive Statistics, Explore. And I'm going to go past descriptives, go to Explore, and have it tell us something about this. Well, it's already going to calculate the descriptive statistics, mean, standard deviation, etc. for the incomes. Now we're going to tell it to break it up by city, okay? And it's going to actually separate it by city and tell us what the means and so on and so forth are by city. Okay, so I'm going to say okay. Okay, let's see what it does for us. Okay, so here we are. See if I can't find it. Gives histograms and everything. So the mean for Chicago is 90. The mean for New York is 89. They're not very different, are they? Right? So I'm thinking that it's going to be tough to prove without a really big sample that these are really different. So let's assume that they are different. Well, actually, 89 is less than 90. You know what I'm going to do? I'm going to go in here, make it even a little bit more dramatic. 40. Let me lower some of these. 40. 45, 45, 60. Okay, let's do it again. Analyze, Descriptive Statistics, Explore. It's already set up, so I'm just going to do it again. Okay, this time, the mean for Chicago is 90. The mean for New York is 81,000. So now we got a little bit of a test here. Can I tell based on these samples, one is, I think, sample size of 29, the other is 27. Can I say with 95% certainty, with 5% chance of being wrong, that the means of these two incomes for city housing for these two cities is different? Well, for that, I need to do a t-test, right? I'm going to compare means. Analyze, compare means. Now, these are independent samples, t-tests. Right? There's two independent samples. So the testing variable, the value that I'm going to find the averages of to compare, the two groups I'm going to find the averages of to compare, it goes in here. Those are the actual incomes. The grouping variable goes down here. So I'm going to pick city, put it down there. It wants me to tell it that 1 represents one city and 2 represents the other city. Okay? And my options again are, do I want this to test this down to alpha equals 1%, in which case I would put 99, or do I want to leave it at 95? Alpha is equal to 5%, 5% chance of being wrong. So I'll leave it at 95, and I'll click OK. And again, it calculates the means and so on and so forth in a box plot. And you can see in the box plot that we can see that New York has a lower median than Chicago. It's more variable, right? I put a lot of low numbers. I put a really low number in there. More variable than Chicago. Okay, so let's see what we found. Found the means, just as we did before, the standard deviation, the standard errors for both of these. Now, interestingly enough, remember we talked about standard deviation? There's a standard deviation for Chicago, and there's a standard deviation for New York. In this case, the standard deviations are really close to one another. So SPSS, seeing that they're close to each other, our general rule is if one is not twice the other, they're close enough to say that we can put all the numbers together to calculate a single standard deviation. In other words, pool the standard deviations, right? So in this case, I would, if I were doing this manually, pool these standard deviations. But SPSS has its own test for that. It actually does a test called the Levene's test for quality of variances. So SPSS actually goes ahead and calculates the t-score for both equal variances assumed, right, equal standard deviations, or equal variances not assumed. Does it both ways, right? So just like everything else that we do, the assumption is that things are the same, and then we have to prove them to be different. Okay, so in this case, equal variances assumed is our null hypothesis. Equal variances not assumed is our alternative hypothesis. Equal variances, not equal variances. So we start with the assumption that we're going to use the top line, equal variances assumed. If we look at the test for equality of variance, the significance, the p-value, tells us the likelihood we would be wrong if we reject that idea and go to the bottom line instead. And in our case, we want that to be less than 5%. In fact, it's 60%. So we don't have justification for going to equal variances not assumed. So we're going to stick with the top line. And if we go across the top line, it calculated the difference between this mean and this mean divided by the pooled standard so about the pooled standard the standard error based on the pooled standard deviation. The difference is a t-score of 1.5. And the degrees of freedom are 54. That's the sum of the 29 and 27, I think it was, and subtract 2, n1 plus n2. Subtract 2 if you go back to the sheets that we have for the how to calculate it manually. So degrees of freedom is 54, and I'll bet, let's see how big a t-score we need to reject the null hypothesis, that the means are equal. Okay, so for 64, okay, for 60, it would be 2.0. For 80, it would be 1.0. I'm going to stick with, I'll be more conservative. I'll call it 2.0. So there's our t-score. Is our t-score larger than 2.0, the critical value of t? And the answer to that is no. So we don't have enough evidence to reject the null hypothesis that the two means are different from one another with 95% certainty, or less than 5% chance of being wrong. Even though they look quite different, it's not, given their variability, it's not enough evidence to be certain to that level. Okay, now SPSS actually goes a step further. Okay, it takes the t-score, and just like we were doing with the z-score to find the p-value, it actually calculates a p-value. See, for us, if we're doing it manually, it's tougher for us to do this unless we use Excel, which has a function in there. I'll show you in a second. Okay, the t-score is 1.528. Okay, so the probability of being wrong, if we reject the null hypothesis, which we already decided that we were going to reject it, right? The probability of being wrong, the probability would be 13.2% or 0.132. So you need two things. You need this to be bigger than the critical value of t, and you need this to be less than 0.05. And they will both happen at the same time. When this is 2.0, this will be exactly 0.05. Okay, so in SPSS, we actually have that advantage. Now, just to show you, in Excel, as a last thing I want to show you, okay, and guys, feel free, I can't stay on much longer, but feel free to email me tomorrow, and I'll try and check in tomorrow in my email and stuff like that, or post on the discussion boards any questions that you might have to specific homework problems or something like that. Feel free to put those up there and ask me, and I'll try and put up an explanation. Also, maybe other students will help out also. The other class, the online class, they really make extensive use of the discussion board. A lot of people get involved in it. So let's say, what was our t-value there? Our t-value there was, let me see if I can't find it again. Our t-value there was 1.528, 58 degrees of freedom. Okay, so if I know my t-value, my t-score is 1.528, well, what is the p-value there? Well, we actually have a function in Excel. It's equal to I think it's t-dist. Let me give that a try. whoops. Yeah, the t-distribution, okay? T-distribution, we can find out what our p-value is by using equals t-dist and putting in the value of t. It's called x there, but it's really the value of t. I'm going to click it in so I don't get it wrong, comma, the degrees of freedom, which were 54, comma. Now we're going to do, we're usually doing two-tail tests, 2 for the number of tails. Let's see if I get the same p-value. And I got 0.132, which is the same thing that I got here. So we can get a p-value from the t-value using Excel. Okay, if we were going to do it for z, instead of t-dist, we would use equals, what was normdist, I think. I'm having a senior moment here. Normdist, right? No, norm sdist, standard distribution. So here you could just put in the t-value. So if that, instead of a z-score, it was a t-score, it was a z-score of 1.528. Okay, what would that value? 1.528. What area would that represent? Now, a little bit different. When you do the z-score, it only gives you the area to the left of that value. Actually, to make this give me a better number, I'm going to put a minus in here. So it only gives me the tail on the left. And if I hit enter, that's the tail on the left. In order to get both tails, I have to double that. Equals 2 times, a lot easier with SPSS, isn't it? Whoops. Is equal to 2 times that number, and it's 0.1265. It's a smaller probability p-value. We are less likely to be wrong because you're using the z-score, and that's only used if you know the population standard deviation, and or you're dealing with a super large sample, a very large sample, right? So this is a larger. You're more likely to be wrong with the t-test than with the z-score. In other words, you're more likely to be wrong if you try and make a prediction with a small sample than with a large sample. Okay, guys, so I'm gonna sign off on that. Send me, like I said, post on the discussions board, or send me some emails. And I was hoping that I'd get more specific questions and stuff like that about stuff on the homework and stuff, so I could direct this a little bit more. But I think that maybe that kind of general review might have helped you out a little bit. But if you do send me some specific problems tonight or early enough tomorrow morning, I might even be able to post a little video solution of them. Okay, especially if there's a problem on the homework that has you stumped. Are slides 14 to 18 independent samples? Slides 14 to 18. I'm not sure what slides we're talking about. You mean on the lecture, the PowerPoints? Kelly? From last Thursday. I have to look at that. Are they 4 independent samples? Let me go take a look right now. Let's get a glance at that right now. So that would be the lecture. Last Thursday.
Monday.
Okay. Last Thursday. I'm a little confused. Thursday was when I did that online session, right? I'm not sure what. Oh, okay, good. You scared me
It's
because
Monday.
the other biostatistics class is on Tuesday, and I just had the terrible dread that I was talking to the wrong class right now. Okay, thank you. Okay, that would probably be this, I guess. 2 sample hypothesis test. Maybe this is the right one. So let's take a look at slides 14 through 18. Okay. Okay, let's see what this is. Okay, so yeah, this is for independent samples test. How do I know that? Because there's 2 X bars here, right? And so this is based on if you don't pool the standard deviations. Matter of fact, might say that. 2 independent samples. Okay, this is if you don't make the assumption that the standard deviations are equal. Oh, hang on a second. I'm getting ahead of myself. This is basically if you know sigma, if you know the population standard deviation, okay, or if you're guessing at it. So yeah, it's a standard error of these two groups. So this is the formula that I believe you would use for if you're assuming that they're not equal. And let's see, and this is the same thing. This is without pooling, right? In other words, the assumption is that the standard deviation of group 1 is not equal to the standard deviation of group 2. This is just another form of that, where they're using sigma instead of standard deviation. When you're doing samples, 2 samples, you rarely know the true population standard deviation. So you're usually in this position, right? So mu2 minus mu1, right? Well, you know that statisticians, when they write this out, they're saying compare the difference to what you think the difference should be. It's kind of a way of notating this, but in reality, when you say the null hypothesis in your null hypothesis, that one mean is equal to the other mean, your null hypothesis, really what you're subtracting here is 0. So you really can just look at this as x bar 2 minus x bar 1 over the square root of the squares over a sample size of the standard deviations of the two groups. Okay, so you can just forget about this part. Functionally, you can forget about this part. So yeah, this is without pooling. That's saying that I'm assuming that these are not the same. Okay, so let me see if I got any more here. And this is the situation where there's not a very big difference between the two standard deviations, and you want to actually pool the standard deviations so you get a better look at it. In other words, you say to yourself, if I got a sample 1 has 30 people in it, sample 2 has 30 people in it, well, maybe I have an advantage by saying, if I assume that they both have the same standard deviation, now I can calculate the standard deviation based on 60 people, not 30 people. So maybe that'll wind up helping me out. So you would use this in the situation. You would use this, calculate pool standard deviation, and put it in there. You would use this in the situation where the two standard deviations are close to one another, and you would use this formula in the situation where they are pretty different from one another. And in general, usually it's that one is double the other is the kind of the cutoff point. Is the two sample z-score only good if n is equal to or larger than 300? In previous courses, in a lot of textbooks, because, and this is going back because a lot of these textbooks are a little bit older. A lot of these commonly used textbooks been around for a while. A lot of times they would say anything over a sample size of 30, you could use the Z table. Let me show you why they say that. Okay, press Z. Okay, if I look at the Z, actually I want to use the T table. Let me tell you why they say that. Agresti T table. Okay, if you look at the T table, for when you got really small samples, look at this, 1 degree of freedom. In other words, a sample of 2. The T is enormous, right? Now remember that for 95% confidence interval, the Z-score is 1.96, right? But and all you need to do is exceed that to be 95% sure that you can reject the null hypothesis. But for a small sample, like a sample size of 5, 4 degrees of freedom, you have to exceed a much bigger number, almost 2.8. But as the numbers get bigger, they get closer and closer to 1.96, right? So if you got a sample of size 30, you're already down to 2.04. You're really close to 1.96. So a lot of the textbooks will say, especially back in the days when we would do a lot of calculations by hand, that if you have a sample size of 30, don't even bother with this. Just use the z-score of 1.96 instead. Now, Levi mentioned in class that you really should stick to very large samples before you jump to the z-score, like 300. Well, if you can imagine, a z-score of 300 would be something like 1.965 or something like that. almost 1.96. The only time it's really, truly 1.96 is when you sample the entire population, right? An infinite number, or by infinite they really mean you have sampled the entire population, so you know what sigma is. So yeah, I'm a little looser on that. I would say if you have a sample of 100, that I would be okay with using the z-score, because look, it's 1.98. It's so close to 1.96 that why bother going to a table and look it up? But on the other hand, software like SAS, SPSS, they always use the t-test. So like even if we had a sample size of 1,000, when you made that table up, it would give you a t-score, not a z-score, and give you a p-value based on the t distribution, not on the z distribution, even if they're only the tiniest bit different, right? So that's really kind of like where that is. So I would look for some guidance in the question that would say, yeah, obviously, if he tells you that the sample size is 300, he's telling you that it's a big sample. You can use a z-score instead of a t-score. Okay. But if he gives you a sample size of 30, right, or 25, or even if he gives you a sample of 64, you might want to stay safe and use the t-table, the t-distribution, with the critical value of t instead of 1.96 when testing your hypotheses. Because unless he gives you in the question some direction otherwise. Okay. Okie doke. If we have a sample size 1, do we have to use the population sigma? If it's a sample size of over 100, I would use 1.96. Okay. But like I said, I don't think that Levi is going to I haven't actually seen the final exam. I don't think Levi is going to trick you that way. And if it is a sample size like around that, I would maybe say, can we assume that it's a large sample and use the z-score instead of the t-score? I would ask. But I don't think I think he's either going to give you a small sample size or a really big sample size and not make you guess on that. Okay, so we're not trying to trip you up. There's only one question on there that I tripped you that was kind of a little tricky on the homework, and one of them I asked which is which is your appropriate outcome for one of the analysis, and it was like accept the null hypothesis, reject the null hypothesis, something else, and none of the above. And the answer happened to be none of the above because you don't accept the null hypothesis. Just because you weren't able to prove the alternative doesn't mean you accept the null, right? Because you weren't even trying to prove that. You don't know whether it's true or not. You say that we failed to reject the null hypothesis, not that you accept it, but you failed to reject the null hypothesis. Okay, guys, good luck on the exam. Like I said, email me because I was hoping that I would get some specific questions so I could help you a little bit more specifically. But email me or post them on the discussion board, and I'll check the discussion board several times between tonight and tomorrow morning. So hopefully I'll be in class for at least part of the class, and I'll get to see you guys again. Bye.